So in an X-ray bipartite, if partite X is unsaturated, then there exists a subset S of X. There exists at least one subset S of X such that mod S strictly greater than NS. This is something we need to prove. So how do we do this? Our assumption is partite X is unsaturated. So what it immediately tells, suppose this is a bipartite graph, and here you see that partite X is unsaturated. So these are the matching edges. This, I should make it red. It will be easier for us to understand. If you so if you see that in partite X, X is unsaturated. So I put this vertex U is unsaturated. All other vertices are saturated. Okay. So we have to prove that in an XY bipartite graph G, if partite X is unsaturated, then there is a subset. So to prove it, what we assume that, suppose this graph, XY bipartite graph, has a maximum matching M, and in spite of maximum matching, it does not saturate X. Okay, it is not a maximal matching. It says it's a maximum matching. The M has a maximum matching and it does not saturate X. Say a vertex U is unsaturated in X. So U is unsaturated in X. Then what we have to prove? We have to prove that, we have to prove, we have to prove that there exists a subset S of X such that mod is greater than NS. So मैं S कैसे क्रिएट करूंगा? So मैं A में एक मैक्सिमम मैचिंग ले लिया इस ग्राफ का such that this maximum matching doesn't saturate X. So in this graph, U is that unsaturated vertex and all other vertices are saturated. Now I choose S, I create S in such a way, S contains U. Along with that, it has set of vertices in X such that, so which are reachable from U through some alternating path. इसका मीनिंग क्या है कि this is my U. I know this is my unsaturated vertex. So I will create S such that U is included in S. Along with that, a subset of vertex of X is also included in S. Which are those vertices? So U से alternating path में जो vertex मैं reach कर सकता हूँ. Say for example, U से alternating path मतलब first unmatched followed by matched edge, like that. So it is unmatched, then matched edge. So this vertex is there in S. Then from U, I start from here, I come here, I go there, I come here, I go there. So this vertex is also there in S. Also, I come from here to here, I go to this vertex. Again, I go by unsaturated edge, I go by saturated edge. So this vertex is there in S. However, these three vertices are not there in S because they cannot be reached. So what is S? U plus set of vertices in X that are reachable from U through some alternating path. Okay, so like this vertex. Okay, say for example this vertex, I can reach from you. I came here and I can go there, but they are not through. They are not alternating path, because this is unmatched edge. This is also unmatched edge. So this is not included there. Okay, so only those vertices are included which are reachable from you through some alternating path. Similarly, T is the set. T is another set of vertices in Y that are reachable from you through some alternating path. जैसे you say ये reachable है, so this is in T. Then I go by matching edge and unmatched edge, so this is in T. From you I came here, I go by, so it is unmatched edge, then matched edge, then unmatched edge. So this is there in. So this vertex also in T. Other vertices are not in T. Okay. Why the other vertices are not in T? Because they are not reachable through some alternating path. Okay. We have to prove that mod of T equal to mod of S minus 1. That is something we need to prove. So the size of T is 1 less than the size of S. And that can be proven by the construction itself. Why? Because except U, how do we prove it? In S, मैं यहाँ पे नहीं लिखा, in S, except U, all other vertices are reachable from U through T through some matching edges. Since these are the matching edges, so matching edges का एक end T में है and दूसरा end S minus U में है. So that is why mod T equal to mod S minus 1. So I will repeat this logic. So except U, all other vertices in S are reachable from U through T through some matching edges. So जैसे this vertex is matched to this vertex is matched to this vertex is matched to this. So that is why T is mod S minus 1. This 1 comes from, since for U, because U is an unmatched vertex, is an unsaturated vertex. So we have proven that mod T equal to mod S minus 1. So mod T equal to mod S minus 1 immediately implies that mod T strictly less than mod S. Now if we prove that the size of T, actually the set T is actually the neighbor set of S, exactly equal to the neighbor set of S, it does mean that mod T equal to mod Ns, and since mod T less than mod Ns, so mod Ns less than mod S. Okay, so basically what I am saying, so mod T less than mod S, and if I prove that mod T equal to mod Ns, so I replace mod T by mod Ns, so it proves that mod Ns less than mod S, and we are done. So that is something we need to prove. So if X is unsaturated, then we will prove that we can find a subset S whose size is greater than Ns. So the thing that remains to prove is mod T equal to mod N. Sorry, this T, this set T is nothing but neighbor set of S. इसका मतलब क्या है? इसका मतलब ये है कि so every vertex in T is matched to some vertex in S minus U by some edges in N. So this logic actually says that T equal to mod S minus 1. So this actually proves that this proves mod T equal to mod S minus 1. Now we have to prove that t equal to ns. Now कैसे हम प्रूफ करेंगे t equal to ns? So first of try to understand what is ns. Ns means neighbor set of S. And what is T? T are those vertices in S. Sorry, T means that is a subset of vertices in Y which are reachable from U. T is a subset of vertices in Y which are reachable from U through some alternating path. Okay. Now the question is, how do we prove T equal to ns? ये अभी तक हम लोगों ने प्रूफ नहीं किया. How do we prove it? Suppose T is not equal to ns. Suppose T is not equal to ns. Okay. इसका मतलब क्या है? S का कोई एक नेबर if T not equal to ns, इसका मतलब there is some edge from S to here. Okay. So मैं इसको थोड़ा सा दूसरा कलर दे देता हूं. Okay. The question is there any edge like this? So what is this edge? What this edge characterizes? So what I'm saying is there, so if T not equal to ns, if T not equal to ns, इसका मतलब ये है कि there exists at least one vertex here which is a neighbor of S and that is not included in T, which is a neighbor of S, neighbor of some vertex in S, but it is not included in. Is it possible to exist? That means, so if I give this vertex name as Y, and if I give the name of this vertex as V, the question is, can Vy exist? अगर T not equal to ns है, definitely Vy may exist. The answer is no, Vy cannot exist. Why it cannot exist? Because if Vy exists, then what it will happen? This is unmatched edge, this is matched edge, and this is unmatched edge. So basically this is an alternating path. So Y must be included in T. If such an edge exists, then Y must be included in T. That is our definition of T, set of vertices in Y that are reachable from U through some alternating path. So if such an edge exists, then Y must be included in T. But that is not there, so such an edge cannot exist. Not only that, if such an edge exists, it says that it is not a maximum matching. Why? Because it is unmatched edge, this is matched edge, this is unmatched edge. If this is an unmatched edge, then this is an augmenting path. Okay, so I cannot say it is a maximum matching, but our assumption is it is a maximum matching. So that is another way we can say that Vy cannot exist. Okay, since Vy cannot exist, we can say that T equal to ns. If T equal to ns, the existence of Vy indicates that the existence of an augmenting path. The existence of an augmenting path, which implies that M is not a maximum matching. So Vy cannot exist. So S cannot have any neighbor in Y minus T. So this is total is Y, this is T. So Y minus T में कोई भी चीज S से neighbor नहीं हो सकता. Okay. Basically, existence of here indicates the existence of an alternating path. The best thing is augmenting such I write an alternating path. Alternating path, which implies that this v must be. This implies that y should be included in P. Okay. So S cannot have any value answer. So we have proved that T equal to NS. So first we have proven T equal to S minus 1, and it means that size of S is greater than T. And now we prove that this T equal to NS. So mod is greater than NS. So we are done. So this proves the whole theorem. So next we will prove another thing. The proof is this: K regular bipartite graph has a perfect matching. Okay. So basically, इसके बहुत अच्छे applications हैं algorithms में. So we have to prove that K regular bipartite graph has a perfect matching. Now, already we have proven this fact. Okay, we will again prove it. Suppose it is a K regular bipartite graph having partite X and Y. So since it is K regular, we can write number of edges in this graph equal to K into mod X. Also, we can write it in other form equal to K into mod Y. So K. So from here we can easily write mod X equal to mod Y. Okay. So K regular bipartite. So first we have proven that if it is a K regular bipartite graph, then both partite has same number of vertices. That is the first thing we need to prove. Okay, and we have proven that. How do we prove? That we count the edges by a single partite X. So it is the X partite, number of vertices is mod X, and सबका degree है K. So number of edges is K into mod X. If we count it from the other point, from other partite, then number of edges will be K into mod Y, and they must be same. So K will cancel out. Then number of vertices in both the partite is same. Now what remains to prove? We have to prove that K, it has a perfect matching. What is the meaning of a perfect matching? Perfect matching means every vertex is saturated in this. So if I do a matching on this K regular bipartite, right, I will always get all the vertex becomes saturated. Okay. So how do we prove it? So basically this system, so it proves that both partite of a K regular bipartite graph has equal number of vertices. Now मुझे प्रूफ करना है कि it has a perfect matching. So हम लोग क्या करेंगे? It is a bipartite graph सो हम लोग ये प्रूफ करेंगे कि we take a subset of it, choose a subset S of X, we took any one of the part either X or Y. सपोज मैंने X पार्टाइड को चूज कर लिया, उसमें मैं कोई भी सबसेट ले लिया, आई डू नॉट नो हाउ टू चूज दिस सबसेट, आई चूज एनी सबसेट S of X. Now how many edges are coming out of S? So every vertex, so mod S is the number of vertices there, so k into mod S edges are coming out of it. Okay, and since all edges, so all these edges goes to the other part at Y, so number of vertices is there is ns. Okay, so ये जितने भी एजेस क्रिएट हो रहा है k into mod s से, इसके जो एंड पॉइंट्स है इन द पार्ट एट y, बेसिकली दैट constitutes your ns. So it must be less than equal to k into ns, because ns is the number of vertices in this neighbor set, and multiplied by k is, so k into mod s. So we have a picture to explain this. Yeah, suppose this is my S. Okay, इससे जितने भी नेबर्स हैं, 1 2 3 4 नेबर्स हैं, नहीं सॉरी, इसके जितने भी नेबर्स हैं, दैट इज NS, एंड k into ns must be greater than this. Okay, so we choose any subset S of X. So how many edges coming out of it? K into mod S. All these edges belong to NS. Okay, so they must be less than equal to k into ns. मैं एक चीज दिखा रहा हूं आप लोगों को, आप ये बोल सकते हो कि नहीं, ठीक है, इट्स करेक्ट. So k will cancel out, so mod s less than equal to ns.
सर ऐसे बोल सकते हैं क्या कि लाइक के मॉडेल्स हो गए, कितने एजेस जो जा रहे हैं इधर से उसके नेबर में, तो जो जा रहे हो तो नेबर में जा ही रहे होंगे वो एज, तो एनएस के किस साइड से अगर एज काउंट करेंगे तो के मॉडेल्स एजेस तो मिलेंगे ही मिलेंगे, बट
एग्जैक्टली उससे ज्यादा ही मिल सकता है. या करेक्ट. सो के मॉडेल्स जितने एजेस हैं उतने नेबर्स नहीं मिलेंगे, क्योंकि दिस, जैसे मान लो this is my S, okay, and suppose this edge is not there, and suppose this edge also not there. Okay, so this is my S. Oh, मुझे तो it is a regular bipartite, right? Okay, I have to. Okay, since it is a k-regular bipartite graph, so इसका अगर मैं like डिग्री 2 बनाता हूँ, तो इसको मैं डिग्री मुझे 2 बनाना ही पड़ेगा. So k into mod s edges are there. तो ये हो सकता है, ये इक्वल हो सकता है, it might be, so like ये इक्वल टू हो सकता है, बट इट मे बी ग्रेटर देन ऑल्सो. तो उतना तो जाएगा ही, उससे ज्यादा भी जा सकता है. So if S is a subset, so S say how many edges are coming out? K into mod S. Those go, and this K into mod S basically reaches to NS. And so इसको मैं कैसे बोल सकता हूँ? So there are, we choose a subset S of X. So the number of edges coming out of it is K into mod S. That is fine. And choose a subset S of X, okay? And number of edges coming out of it is K into mod S. So can anybody tell why it would be right? This statement is right. The given part is only, it's a K regular bipartite graph. I choose any subset S of X. So basically my thing is, if I prove this, if this is correct, then mod S less than equal to NS. So Hall's condition is verified. So it means that X, the partite X is saturated. Similarly, the same logic, by same logic, I can prove that partite Y is saturated. So if both partite X and partite Y is saturated, means it is at it has a perfect matching. So the actual proof boils down to the proving this fact: phi K mod S less than equal to K, sorry, yeah, K mod S phi less than equal to K into NS.
Sir, like I'm telling, like if we count number of edges from partite set S, though there will be K mod S edges, right?
Right.
And all the edges will have all those edges will have a neighbor. Means all the edges which we are counting will be included if we count the edges from NS, right?
Yeah.
So the total number of edges from, if we count from NS, will be
Right. Basically, it's a edge. Right. मैं vertex से correct. You are right. Correct. Yeah. So basically, S is a subset of X. So S number of vertices there. So how many edges are coming out of it? K into mod S. This many edges are coming out of this S, and this somehow this number of edges uh, again. Can you repeat again? So map fits it.
Sir, like K mod S edges are coming out. So
Yeah.
NS will be for every edge we will get a neighbor, right?
For every edge in case, I will get a neighbor, but they may not be distinct.
Yes. So, so they may not be distinct, but like if we count the number of edges from the neighbor side, that should include those edges, right?
Those should include these edges also.
Yes. If we count
Right.
the number of edges from the neighbor side.
Yeah. Right. Yeah, correct. So basically, number of edges coming out of S is into mod S. These edges are subset of into mod S. Will always be a subset of K into ns. So we can write this edge will always be a subset of K into ns. So this can be written, and from here we can do. So if this is true for, so it is for all subsets, for any subset S of X, we have proven that mod S less than equal to ns. So what Hall's condition says, what Hall's theorem says, if for all subset S of X is mod S less than equal to ns, then the bipartite graph saturates X. So this implies that K regular bipartite graph G saturates X. The same logic, the same logic can be given to partite Y to prove that G saturates Y. Since X and Y both partite are saturated, then it is a perfect matching. Okay. Since no, it is also not correct. सब वर्टेक्स सैचुरेट हो गया मतलब, yeah, since both partite are saturated, so G has a perfect match. Yeah. Now we will explore few more interesting properties. Uh, just give me a break for 2 minutes, then we'll come back. Okay. So now we will move to an dual property thing, and this is very important topic in matching. This is called min-max theorems. Okay. So basically, when we study bipartite graph, when we study any bipartite graph, we know that what is a bipartite graph. Bipartite graph is such a graph which doesn't have odd cycles. Okay. If the graph have, so bipartite graph may have cycle, may not have cycle. If it has cycles, then it must be an even cycle. It cannot have odd cycles. So basically, bipartite graph is a special kind of graph which doesn't have odd cycles. So it constitutes a large class of graph. And what happened? We know that finding vertex cover independent set ESF in a graph is an NP-complete problem. Now, when people find NP-complete problems, they try to devise algorithms which may be an approximate algorithm. Okay, and another class is maybe for a general class of graph, vertex cover and independent set problem is an NP-complete problem, but for a subset like finding vertex cover and independent set in a bipartite graph is in P. So there is a polynomial, so that is why it's selected good news. So it's like so if somebody says you are given a bipartite graph and somebody asks you to find the vertex cover on an independent set, then you can do that in polynomial time. Okay. So before we go to these algorithms, how to find it out, why it is in P and how. So first we need to know few terminologies. So alpha G. What is alpha G? It says size of the maximum independent set. It is not independent set. It is the size of the maximum. So for a given graph G, alpha G, alpha prime G, beta prime G is constant. This is a number. It's an integer. So size of the maximum independent set is alpha G. Alpha prime G is size of the maximum matching. Beta G is basically size of the minimum vertex cover. Beta prime G is size of minimum edge cover. Okay. So टू कीप तो ये चीज आपको याद करना पड़ेगा. ये जो नोटेशंस है ये आप लोगों को याद करना पड़ेगा. नाउ व्हाट इज द इजीएस्ट वे टू कीप दिस थिंग्स इन माइंड. सो अल्फा स्टैंड्स फॉर मैक्सिमम एंड बीटा स्टैंड्स फॉर मिनिमम. सो यहाँ पे दोनों अल्फा है, दोनों कितने मैक्सिमम है. बीटा अगर प्राइम है सो इट इज रिलेटेड टू सम एज प्रॉपर्टी. अगर नॉन प्राइम है तो इट इज रिलेटेड टू सम वर्टेक्स प्रॉपर्टी. So alpha means maximum and it is there is no prime here, so it is maximum related to some vertex. So maximum vertex related क्या हो सकता है? Maximum independent set ही हो सकता है. Similarly beta is minimum. Minimum vertex के साथ हम लोग क्या पढ़े हैं? Minimum vertex cover. Okay. Similarly alpha is maximum, prime is edge. So maximum edge हम लोग जो पढ़े हैं अभी तक maximum matching. So this is a crude way of recalling things. So beta stands for minimum and is the minimum edge. So basically size of minimum edge cover. Okay, so that is how we can recall all these terms. What so alpha stands for maximum and prime stands for any edge. Non-prime stands for any vertex. And beta stands for minimum. So ये चीज याद रखोगे तो ये चीज याद रखना easy रहेगा. तो अभी हम लोग कुछ थ्योरम्स पढ़ेंगे, बट ये नाम के नाम थ्योरम है. बेसिकली बेस्ड ऑन दिस थ्योरम्स यू कैन डिवाइस द एल्गोरिथम्स, यू कैन कोड आल्सो. सो फर्स्ट we today we discuss about this good news. So min max properties for bipartite graph we will study, and we will prove two important theorems. The first theorem proves that, which is known as Koenig and Egerberry theorem. This is a famous theorem in the history of graph theory. Okay, and it changes a lot of things. So we will find what changes it has done. So later. So what Koenig and Egerberry proved that For a bipartite graph, the size of the maximum matching is equal to size of the minimum vertex cover. That is something they have proven. And so next what we will prove that now our objective is to prove that for a bipartite graph, size of the maximum matching equal to size of the minimum vertex cover. Now first we think about the general graph. कोई बाइपार्टाइट में कोई एक जनरल ग्राफ में इन दोनों का क्या रिलेशन है, व्हाट इज द रिलेशन बिटवीन अल्फा प्राइम जी एंड बीटा जी. नाउ फॉर ए जनरल ग्राफ, ठीक है, क्या हो सकता है, आपने एक मैचिंग, सो फॉर एनी ग्राफ, what is the relation between maximum matching and minimum vertex cover? So the answer is as follows. जब हम लोग मैक्सिमम मैचिंग देखते हैं, कोई भी मैक्सिमम मैचिंग, हाउ दिस मैक्सिमम मैचिंग लुक लाइक? This maximum matching is looking like a set of pairwise disjoint edges, right? A set of pairwise disjoint edges. Or what is my vertex cover? Vertex cover means a subset of vertices which cover all the edges. Cover means a subset of vertices such that every edge has an endpoint to that subset, right? तो अगर मैं, ये मेरा मैचिंग के मैचिंग है, तो द साइज ऑफ द मैचिंग इज 3. सो वर्टेक्स कवर एटलीस्ट इतने तो हो गए, मतलब फॉर ये दोनों एज के लिए सेम वर्टेक्स कैनॉट बी रिस्पॉन्सिबल फॉर कवरिंग देम. So for each edges in matching, so basically what I am trying to say here is, for each edge, sorry, to cover an edge in matching, is separate or I should write single vertex in a vertex cover and cover two edges of a matching, right? तो इस एज के लिए एक वर्टेक्स लगेगा, इस एज के लिए अलग वर्टेक्स लगेगा, इस एज के लिए अलग वर्टेक्स लगेगा. तो वर्टेक्स कवर के जो साइज होगा कोई भी ग्राफ में, that will be at least the size of the matching. So in any graph, single vertex cannot cover two edges of a matching. It implies that in any graph, size of the maximum matching less than equal to size of the minimum vertex cover. ये बहुत इंपॉर्टेंट एक ऑब्जर्वेशन है. ओके, तो हर एक एज के लिए एक एक अलग वर्टेक्स लगेंगे. तो इतने तो वर्टेक्स कवर में वर्टेक्स लगेगा ही, इसके अलावा भी लग सकता है. जैसे मतलब मिनिमम इतना लगेगा, उससे ज्यादा भी लग सकता है. Now what we are trying to prove is like this. तो ये यहाँ पे लिखा गया है. You have to prove that if G is a bipartite graph, then size of the maximum matching equal to size of the minimum vertex cover. But in any cover, how vertex cover is related to matching? Vertex cover, the size of the vertex is always greater than equal to size of the matching. And why that is so? Because in a matching, the edges are pairwise disjoint. And to cover each edge, a distinct vertex is required. In other words, the same vertex cannot cover two edges in a matching. Like this. Okay. So, एक ही चीज लिखा गया है, कोई बड़ी बात नहीं है, छोड़ दो. सो वी नो दैट अभी मुझे प्रूफ करना है कि बाइपार्टाइट ग्राफ के लिए ये ग्रेटर देन इक्वल टू नहीं होगा, ये इक्वल टू होगा. हाउ डू यू प्रूव इट? सो हम लोग क्या करेंगे? सो दिस इज ट्रू फॉर एनी ग्राफ. ये लाइन मैं जब बता रहा हूं, ये बहुत अच्छे से सुनो. Since it is true for any graph, vertex cover, size of the minimum vertex cover is greater than equal to size of the maximum matching. If this is true, then it is also true for bipartite graph. So if G is a bipartite graph, also we can easily write that size of the minimum vertex cover is greater than equal to size of the maximum matching. हम लोग directly ये चीज लिख सकते हैं. Now, अगर हम प्रूफ कर दें कि in a bipartite graph the size of the minimum vertex cover is less than equal to size of the maximum matching, then both this inequality अगर simultaneously hold करना पड़े, then they must be equal, right? So how do you prove this next statement? So first statement we already proven. So this statement already we have proven. We have to prove the next statement. If G is a bipartite graph, then the minimum vertex cover is less than equal to the size of the maximum match in a bipartite graph. अगर मैं ये proof कर देता हूँ, then both this inequality to be satisfied simultaneously, they must be equal. Okay. So to prove it, to prove this statement, so this is our objective right now. To prove this statement, what we do, so now we start to prove this Koenig-Iger-Very theorem. That given a bipartite graph G, we have some minimum vertex cover. Okay. Now, from this minimum vertex cover, if we construct a matching of the same size, then we are done. Okay. Because so कैसे होगा? So now our objective is to prove this statement, and to prove it, what we are trying to do, suppose in a bipartite graph G, somebody has given me the minimum vertex cover, some minimum vertex cover. From that, okay, from that we construct a matching of the same size. Same size का मैं एक matching बना देता हूँ. Now since it is any matching, I am not saying it is a maximum match, I am saying it is any matching. Now this matching must be less than equal to this matching. So actually the matching we constructed, the matching we constructed must be less than equal to the maximum matching. So by this two statement, we can say that मिनिमम vertex cover is less than equal to maximum matching. So minimum vertex cover से हम लोग कुछ एक मैचिंग बनाए and that matching must be less than equal to size of the maximum matching. So minimum vertex cover is less than equal to size of the maximum matching. That's how we prove that this statement. So the thing that is remain to prove is how to do this part. Somebody suppose given a bipartite graph, somebody gives me this minimum vertex cover, how we can create a matching of the same size. That is our objective. So to do this, okay. So मैं कुछ लिखा हूँ नहीं तो मुझे लिखना पड़ेगा फिर. कुछ लिखा नहीं है. Okay. So how to prove it? So abhi the task that remain with us, that is remaining is how we construct a matching of size equal to the minimum vertex cover. So this is how we create it. So it is a construction. So suppose this is a bipartite graph, not suppose it is a bipartite graph, and Q is the set of vertices which constitutes the minimum vertex cover. Now what is Q? This Q is the set of vertices. Some of them are chosen from X and just a minute. So I have to write here. Suppose Q equal to R union T is the minimum vertex cover. Minimum vertex cover. Now this is my R and this is my T. So what is R? R is the set of vertices from partite X which is there in the minimum vertex cover. T is the set of vertices from Y which are included in the minimum vertex cover. Now what I do, I create so okay. Now, so T is the set of vertices from Y, which is the minimum vertex cover. R is the set of vertices from X, which is in the minimum vertex cover. Now I create two bipartite H1 and H2. H1 and H2. Construct two bipartite subgraph of G, H1 and H2. How? So what is H1? H1 is H1 has vertices R union y minus t. ये T है, T के अलावा जितने भी वर्टेक्स हैं R के साथ इस वर्टेक्स का मैं एक बाइपार्टेट सबग्राफ बना देता हूँ. Similarly, H2 is created as T union x minus s, x minus r. So from this minimum vertex cover, construct two bipartite subgraphs of G, namely H1 and H2. And what is H1? H1 has the vertex. So H1 is it is not a bipartite, it's a bipartite induced subgraph. Okay. Why it is induced, I will tell. So basically, this is my R. These vertices belong to the vertex cover, and this is T. This belong to the vertex cover. Now y minus T is these vertices. So इसके बीच में जितने भी edges हैं, I will take all the edges. So ये subgraph अगर लिखते तो ये subset of edges I can choose. If it is an induced subgraph, I have to take all the edges between R and y minus T. All the edges. This is all these edges. And which edges are excluded? These cross edges are excluded. Like this edge and this edge, they are excluded. So just give them a separate color. So this and also this is also cross. So R से T तक जो एजेस है, ये एजेस सिर्फ एक्सक्लूडेड है इसमें, क्योंकि इट इज इंड्यूस सबग्राफ बिटवीन R to y minus T and T to x minus R. सो ये सब एजेस, बाकी जो एजेस है ये सब इंक्लूडेड. नाउ मुझे प्रूफ करना है कि H1 में, in H1 so now what I have to prove. So मुझे करना क्या है, मुझे ये प्रूफ करना है कि H1 में, H1 बाइपार्टाइट जो सबग्राफ है, इसमें जो मैचिंग होगा उसका साइज होगा mod of R, एंड H2 में अगर मैं एक मैचिंग क्रिएट करता हूं, कोई भी मैचिंग क्रिएट करता हूं ऑफ साइज mod T, दैट इज समथिंग आई नीड टू डू राइट नाउ. दैट मींस इस H1 जो बाइपार्टाइट सबग्राफ है, R will be saturated. Okay, so what I have to prove that now objective is to create a matching of size mod R for H1 and mod T for H2. This is my objective. If I am able to do this, then Q is the size of the minimum vertex cover, and if mod R is the size of the matching and T is the mod T is the size of the matching in H2, then T plus R gives a total matching, gives a matching of this graph. Okay, so our objective, what was our objective? Our objective is to create a matching of the same size. Q size का, mod Q size का मुझे एक मैचिंग क्रिएट करना था. ओके, तो मेरा अभी ऑब्जेक्टिव जो हो गया कि मैं mod R साइज का एक मैचिंग में क्रिएट करूंगा फॉर द इंड्यूस सबग्राफ H1. In a similar fashion, I do this to create this matching for the subgraph H2 of size mod T. तो मैं एक के लिए अगर मैं ये दिखा देता हूँ कैसे मैं कर रहा हूँ, तो इट इज इक्वली एप्लीकेबल टू द अदर सबग्राफ H2. So to prove that, okay, so what we do, so we have to prove that H1 has a matching that saturates R into Y minus T, and H2 has a matching that saturates T into X minus R. That is something we need to prove. So prove it like this. We choose a subset S of R. We choose a subset S of R. We consider the neighbor of S in the subgraph H1, which is contained in Y minus T. तो S के जो जो neighbors हैं, which belongs to this. So S का कौन कौन सा neighbor H1 में है? ये H1 में है, ये H1 में है, ये भी है, ये भी है, ये भी है. ठीक है? We won't include this two because it says that for each S subset of R, we consider only those neighbors which is contained in Y minus T. Now if ये जो neighbor set मैं create किया, if mod of मुझे अभी क्या प्रूफ करना है कि mod S, मुझे प्रूव ये करना है, तो मुझे prove that H1 has a matching that saturates R, and since H1 it is a bipartite, that saturates R. तो इसका मीनिंग ये है कि अगर मैं ये प्रूव करते तो इसका मतलब इट क्रिएट ए मैचिंग ऑफ साइज मॉडल, बिकॉज आर को सैचुरेट कर रहा है. टू प्रूव, मैं इसको ऐसे लिखता हूं, टू प्रूव दैट bipartite of H1 has a matching that saturates R, we choose a subset S of R and NH is denotes the neighbor of S in H1. Now मुझे प्रूफ क्या करना है? मुझे ये प्रूफ करना है कि mod of मुझे प्रूफ करना है कि दिस इज स्ट्रिक्टली ग्रेटर देन इक्वल टू मॉड ऑफ एस। मुझे प्रूफ करना है व्हाई दिस इज ट्रू। इफ दिस इज नॉट ट्रू, if NH1s less than S. Now question is it possible? The answer is no. Then we can create a smaller vertex cover by replacing S by NH1S. So what we are claiming, we choose any subset S of R and NH1S is a neighbor of S in this Y minus T. Our claim is that A set either greater than, size of this set will be greater than or equal to the size of S. Why this is so? If this is not true, then we can create a smaller matching, smaller vertex cover. So अगर NH1S छोटा है, इससे छोटा vertex set है, तो मैं ये दो, सपोज यहाँ पे दो है, यहाँ पे सिर्फ इन दोनों का जो नेबर है वो सिर्फ यही है, कोई एक सिंगल वर्टेक्स है. That is not possible, because if that is so, then we will replace these two vertex of Q. ये दो वर्टेक्स को अलावा हम लोग इस वर्टेक्स को चूज कर लेंगे and we arrived at a vertex cover of less size than the minimum vertex cover. So that is not true. So it is never possible. If NH1 is less than S, then we can create a smaller vertex cover by replacing the vertices in S by the vertices of NH1s. So it is always true. NH1s must always be greater than equal to mod S. Since it is for any S, for all subset S of R, mod S less than equal to NH1s. So, and it is a bipartite graph. So we say that this bipartite graph must saturate R. Okay, that is how we, in the same logic, we can prove that. To prove that in this bipartite graph H2, T is, all the vertices in T is, all the vertices in T are saturated. So that's how we create a matching of size mod T plus mod R. Okay, and which is nothing but mod Q. Now the thing that is another observation is, can there be any edge from X minus R to Y minus T? ऐसा कोई एज क्या रह सकता है कि X minus R से NH Y minus T तक? The answer is no. क्यों? Because if such an edge exists, then this edge cannot be covered by R and T. So the observation is, from X minus R to Y minus T, no edge can exist. The reason is, if such an edge exists, then R union T cannot be a minimum vertex cover, because this edge cannot be covered by any of this. Okay, so such kind of edge doesn't exist. So if we look at the proof in this form, we choose S as a subset of R. We consider the set of vertices in H1 which are neighbor of S. If NH1S is less than S, then we can substitute NH1S for S in the minimum vertex cover Q to obtain an even smaller vertex cover. Okay, so that is not possible, since NH1S covers all the edges incident to S that are not covered by T. But Q is the minimum vertex cover, so NH1S is greater than equal to S. So what I have told so far. For all S subset of R, hence H1 has a matching that saturates R. So applying the same argument, you can say that H2 also have a matching that saturates T. Since H1 and H2 are disjoint, the two matching together form a matching of size Q. Now the question is why H1 H2 are disjoint? इसीलिए H1 H2 disjoint है कि because the way we created it, that's the simple thing. So so yeah, so it proves for this. So from Hall's condition, from Hall's theorem, R is saturated. तो मॉडरेट साइज का मैं मैचिंग मुझे मिल गया H1 में, सिमिलर लॉजिक में मॉड टी साइज का मैचिंग मिल जाएगा H2 में. So we can create the matching of same size. So that is how so no edge exists from X minus R to Y minus A, otherwise R union T cannot be a minimum vertex cover. So this kind of edges cannot exist. Okay. So today with this I end today's class, and that's all.
Thank you, sir.